The answer is found by going back to the titration equation way at the top. Notice the products you get are nice neutral water and acetate. Is acetate on your list of spectator ions? No, it is not. Acetate is a negative ion, which means it's a potential base, and sure enough, acetate will grab a hydrogen off of water and form some extra hydroxyl ions. Isn't that kind of weird? So even though it's neutralization between acid and base, we get some extra hydroxide. Therefore, that's why the pH is basic. Interesting, don't you think? Okay, so here we are so far. We've got the starting pH of 3 on the weak acid. Then it went to 5, then 6.7, and now notice the endpoint is 8.85. It's above 7. So for a strong acid, strong base, it's 7, which you'd expect. For a weak acid, though, you're going to get above 7. It's going to be 8.5. It's actually the pH at the end point. Now to finish this up, I want to do 2 more points with you. Let's do 1 milliliter above or beyond the end point. So the end point is 50 milliliters. Let's add 51, and then we'll also double the end point and get these 2 pHs, then we'll have the overall shape on this. Okay, so let's go through the math on this. So first of all, we've got the titration equation written at the top, and then we're going to take 10th molar, 50 milliliters of the acid. We always have that in the flask. And now we're going to take 10th molar hydroxide, but Berg wants to go a little bit past the endpoint, so we're going to add 51 milliliters of it. Taking dilution into account, the total volume is pretty close to 100. So taking the dilution factor into account, the diluted concentration of the acid is 0.05 molar, and the base is 0.051 molar. Okay, and notice in the completion step, the acid's a limiting chemical, and so we end up with a little bit of excess of base. Now, do you see this wonderful blue line here? What I'm telling you is, once you're past the endpoint, you can base the pH on the excess hydroxide. You don't have to do a completion step or an equilibrium step. You can go right to the excess hydroxide. So 0.001 molar is 1 times 10 to minus 3. So the pOH is 3, subtracting from 14, that means the pH is 11. Okay, now let's go to the bottom one. Let's double the endpoint. So again, titration equation is given. Okay, we have 10th molar, 50 milliliters of the weak acid. 10th molar, now Berg wants you to add 100 milliliters of sodium hydroxide. So the total volume is 150 milliliters. So taking dilution into account, the concentration of the acetic acid is 0.033 molar, and double that would be the hydroxide, 0.006 molar. And in the completion step, you push it all the way to the right. So all the acid is neutralized, you have 0, and we have some excess hydroxide, and we can base the pH on the excess hydroxide. So let me check the math on this with you. So 0.033 molar is the hydroxide. So 0.033. I will take minus the log of that. I get a pOH of 1.48, subtracted from 14, and the pH is 12.52. Now, I want you to notice that if you look at the last 2 pHs, the pH 11 and 12.52, they're the same for the strong acid and the weak acid. So it's different until you get to the end point, and then after that it's the same. So once you pass the pH of the end point, the strong acid and the weak acid and strong acid are exactly the same. Okay, if you wonder what Berg does when he has nothing to do, this is what I did last night. I decided to work out the titration curve of 4 different acids, and you see all these points down here? That means I calculated 100 different points on each of these. Now, this chart is really interesting because if you look at the bottom one, that's one we did on Tuesday, strong acid versus strong base. If you look at the purplish red one, that's the one we just did. Okay, and as we promised you, for a weak acid, the whole curve is higher because we're getting less acid produced by the weak acid, therefore the pH is higher. Then I went to a case of A of 10 to the minus 7, and again it's raised even more. And then I really went wild. I went to a case of A of 10 to the minus 9. So notice they all have pretty much the same shape, except as the acid gets weaker, the curve gets pushed up. Now here's the main thing I really want you to notice. If you want to detect the endpoint, it gets harder and harder to detect it because the slope or the break is not as sharp. In other words, for a strong acid, strong base, look how the pH changes so much with a half a drop from your burette. For a pH of a case of A of -5, the break is not quite as good, but still pretty good. Notice the break on a 10 to -7, it gets even smaller. And notice for a 10 to -9, it's really hard to detect it. Now, phenolphthalein is the indicator of choice. Remember, phenolphthalein changes at pH of 9. So notice it'll work for the case of A of the strong acid, case of A of 10 to -5, 10 to -7. Notice for 10 to -9, it doesn't work very well because 10 to -9 up here, the change is very small and hard to detect. Now, we can solve anything in chemistry. So how do you think chemists got around this? They decided to do the titration not in water, but in another solvent. See, the problem with water is water gives off hydrogen also, so it competes with the acid. So the trick is you pick a solvent that doesn't compete with the acid as much. For example, you'd actually do the titration in ammonia. So nothing we'll do in this course, but I hope in advanced chemistry class you'll study a titration curve where you use a non-aqueous solution. But the point we're trying to make here is the acid gets weaker, it gets harder to detect it. But notice phenolphthalein does a pretty good job on most of them. Okay, you've now mastered what I think is one of the hardest things in the course, and that is a weak acid versus strong base titration curve. Okay, and on an exam, I wouldn't make you do the whole titration, but I might pick out one particular point and ask you to calculate the pH. Now that you've seen this based on first principles, we're going to learn the quickie method, which I call the sketch method of getting the shape of a weak acid titration curve. Now, what I've marked on this chart are the 6 points you're going to learn on the sketch method. Okay. Point number 1 is you're going to learn how to get the pH halfway through the titration. Okay. And that should take you on an exam about 5 seconds to get it. It's so simple. I'm going to show you how to get it. It should take you 5 seconds to get it. Now, points 2 and 3 are going to take you another 5 seconds. Okay. And just to give you an estimate, point 2 is about 10% of the way through the titration. Point 3 is about 90% of the way through. Those are going to be really easy also. So points 1, 2, and 3 are going to be really simple. Everyone's going to get them. Now, point 4 at the start, you're going to have to work a little harder to get that one. Point 5, the end point's going to be the hardest one of all. And then point 6, double the end point's going to take a little time also. But 1, 2, and 3 are going to be really easy in the sketch method. 4, 5, and 6 take a little bit longer, but not too bad. So I'm now going to take you through the sketch method of getting the shape of a weak acid titration curve. Okay, so to illustrate the sketch method, what we're going to have then is we're going to have 10th molar weak acid HA, 70 milliliters of it, and you're given the case of A for that at 10 to the -8. Now, I don't know why I did it, but it might be useful. Notice I also wrote down the P case of A, but you could get that yourself. If the case of A is 10 to -8, then the P case of A would be 10 to the 8th. And we're going to titrate it with 10th molar sodium hydroxide. Okay, now we've got the good old equation, molarity times volume equals molarity times volume. So plugging the numbers, 0.1 times 70 equals 0.1 times X. Yeah, obviously X is 70. That will be the endpoint of this. Okay, now let's write down the titration equation. Okay, so you've seen this before. Okay, so molecules of the weak acid with hydroxide gives you water and the conjugate base. Okay, now you're going to need the case of T, and think alphabetically. A over W will get you the case of T. So the case of A is given 10 to the -8. Case of W is 10 to the -14. 10 to the +6. Good double check. Titration equations will always be positive. Now, with the sketch method, we don't have to work with molarities. You'll be happy to hear that. We can work with percentages. So let's call the amount of the acid at the beginning 100%, and we're now going to add 50% of the required base. So we're first going to find out the pH halfway through the titration. So let's work with percentages. Okay, in the completion step, all the base gets used up because it's the limiting chemical, and 50% of the acid is still going to be there. Now, on the product side, we don't care about water. And notice if you use the balance equation 1 to 1 to 1 to 1, so the gain of the conjugate base is going to be 50%. So look at the completed concentrations. 50% of the acid will be in its original form, and now 50% has been converted to the conjugate base. So I've written the change step also. Now look at the equilibrium concentration. So here is the weak acid, 50% plus X, hydroxide, and its conjugate 50% minus X. Okay, as we discovered before, it's faster to get to pH by using not the titration equation, but the dissociation of the weak acid itself, which is written on the right-hand side here. So plugging in the equilibrium concentrations from before, 50% plus X, Y for the hydrogen concentration, 50% minus X for the conjugate base. Plugging the mass action expression, notice what we have. So the K sub A is 10 to the minus 8 is equal to hydrogen times A minus over the molecules of the acid. Now notice how nice the math is. If you ignore the X's, the 50% cancel out, and Y, which is the hydrogen concentration, is equal to K sub A, which is 10 to the minus 8. So here's something worth memorizing. It's that easy. The pH halfway through the endpoint is always equal to the pK sub A. In this case, it was 8. Now, this actually is part of experiment number 9. You're not going to do the experiment, but I'm going to give you the pH halfway through a titration. And what I'm indirectly giving you is I'm giving you the pK sub A of the acid, which is the goal of that part of the experiment. And I'll explain in the lab, when we do the lab, I'll explain how you actually do the experiment so you set it up so you're halfway through the titration. So anyway, on the exam, you don't have to do all this math. I want you to automatically know that the pH halfway through the reaction is the pK sub A, which is going to be, in this case, it was going to be 8. Okay, now, you found a very easy one to get, and that is halfway through the titration. The next easy one goes like this, okay? So we're going to work with percentages again. I've written the titration equation above, and you also have the K sub T for it. Now, let's work with percentages. So again, let's call the starting amount of the weak acid 100%. And now, strangely enough, I want you to find out the pH when we've gone 91% of the titration, which sounds like kind of a strange number, but you'll find out why later that's really a great number. So again, let's work with percentages. So the completion step is to the right. The limiting chemical is the hydroxide. It's used up completely. We end up with 0. Now, how much acid is unreacted? 91 subtracted from 100, we have 9% left. And now look on the right-hand side. We have a 1 to 1 to 1 reaction. So the gain of conjugate base is 91%. Okay. Now, change step, we've got the X's there. Okay, so at equilibrium, we've got 9% plus X represents the acid, and 91% minus X represents the conjugate base. Okay, bring these down to the other system that's working, which is the weak acid breaking up into hydrogen and conjugate base, and the given K sub A was 10 to the minus 8. Okay, so plugging in the equilibrium concentrations of 9% plus X, Y, and 91 plus minus X. Plug this in the K sub A, ignore the X's, and no. Let's kind of approximate here. 91 divided by 9 is pretty close to 10 to 1. Okay, now let's solve for Y, which would be the hydrogen concentration. It is 10 to the minus 8. Okay, so look at the rearrangement, see if you agree with it. So Y is equal to 10 to the minus 8 times 1 divided by 10, which is 10 to the minus 9, and that means the pH is 9. Okay, now, what's so good about this?